Hello everyone. We want to prove this statement. Let G be a noncyclic group of order p squared, where p is a prime integer. Prove that the order of each non-identity element of G is p. Recall that we can say that a group G is cyclic if we can find an element A of G that generates all elements of G. This means that G is equal to the group generated by element A. And furthermore, we can say that the order of G must be equal to the order generated by A. So we have this assumption: let G be an uncyclic group of order p squared where p is prime. And because we want to prove that the order of each non-identity element of G is p, we suppose that A is a non-identity element of G. And since G is non-cyclic, this means that uh, the order the group generated by A is a subgroup of G. So the group generated by A must not be equal to G because G is non-cyclic. So it must be a subgroup of G. And we can say that of course we can say that the order of the group generated by A is not equal to the order of G. Otherwise, we can put here otherwise the order generated by A, the order of the group generated by A is equal to the order of G. And this would imply that G is cyclic, right? So after that, we will be using the Lagrange theorem, which we can find this theorem in Hungerford because I am using the Hungerford book right now. So the Lagrange theorem states that if H is a subgroup of a group G, then the order of G is equal to the product of the order of G and the relative index of G in H. In particular, if G is finite, the order of A in an element of G divides the order of G. So what I will be using here is this one. It is we can say here that every subgroup of G must divide the order of G. So in here we know that the order generated the group generated by A is a subgroup of G. And so by Lagrange theorem, the order of the group generated by A divides the order of G. So we know that sorry the order of G is p squared. So we can say that the order of the group generated by A is equal to 1 or p, because 1 and p is 1, p and p squared are the only divisors of p squared. It must be divide the order of G, right? So we have these possibilities. It's either 1 or p, because or p squared, say, or p squared. But we can eliminate the possibility that the order of A is the order of A is 1, because our element A here is non-identity, right? So this one here is not, we can exclude this possibility. And of course, because it is non-cyclic, the order of A must not be equal to the order of J. So this one here will be eliminated. So the possibility, we have no choice but to say that the order of the group generated by A is equal to P. And that would be the end of the proof.